Okay, good afternoon, everybody. I'm Indrajit from SPMS, and I welcome you all to this NTU Discovery Science seminar. This seminar is jointly organized by the Institute of Advanced Studies and Graduate Student Council from SPMS, EEE, and SCE.
I'm using this button. You can click first.
So today we have a speaker. We have Professor Wong Liang Jie from the School of Electrical and Electronic Engineering. So Professor Wong, he did his undergraduate at UC Berkeley, then he did his MSc and PhD from MIT. Before joining NTU, he was a postdoctoral fellow at the mathematics department of MIT. And his research interests are into nanophotonics and X-ray photonics and nanophotonics. He has had his work published in leading papers like Nature Physics, PRL, and Science Advances. Without further ado, let's give the stage to Professor Wong. We are very excited for his talk. Professor Wong.
Hello. Oh, this is working. Yeah, so hi everyone. Thanks for coming and thanks for the introduction and also the invitation here. So I would like to begin this talk, by testing you guys to see if you guys recognize these common appliances, right? So I'm sure nobody has any problems identifying the appliance on the left. That's just your light bulb. But how many people know what is the appliance on the right? Let's have a show of hands. Yes, please.
I think West is a vacuum tube.
Yes, vacuum tube is very, very close. Specifically, it is an X-ray tube. And for those of you who don't know what an X-ray tube is, it is simply a light bulb that produces X-rays. Okay, and a very glib way that I thought of comparing and contrasting these two appliances is to say that the light bulb lets you see things, but the X-ray tube lets you see inside things or into things. Okay, so the X-ray tube was actually invented in 1895 by Wilhelm Conrad Röntgen, who also discovered X-rays at exactly the same time. And for his work on X-rays, he actually got the inaugural Nobel Prize in Physics. Right, so what did he actually do in his experiment? In the first place, he wasn't interested in X-rays to begin with. In fact, he didn't even know that they existed. Nobody knew. Right, but he was very interested in studying electrons, which were known then as cathode rays. Right, and how do you produce a stream of high energy electrons? Well, you have a glass tube such as what is shown up here. This glass tube is evacuated, meaning that we have removed most of the air molecules inside the glass tube so that there is now a vacuum inside the glass tube. It is also correct to call it a vacuum tube. There are two electrodes, the anode and the cathode, connected on either end of this vacuum tube, and when the voltage is applied, basically electrons are shot from the cathode towards the anode, and they gain energy as they traverse the electric potential, right? So this is how Röntgen produced a stream of electrons, aka cathode rays, that he was interested in studying. The side effect, the problem, actually something he was trying to avoid, is the fact that these cathode rays would bombard, or these electrons would actually hit the glass walls, and they also hit the cathode, and as a result it produces visible and ultraviolet radiation, which he wasn't interested in. He only wanted the electron beam. And in order to block the visible and ultraviolet rays from coming out, and also any stray electrons coming out from the sides, he basically put this black cardboard insulator at the side of the tube. In fact, he enclosed the entire tube inside this cardboard box. But to his surprise, a nearby screen covered in barium platinocyanide was glowing. It was glowing in a way that could only be accounted for by the fact that electromagnetic radiation was falling upon it. Yet there was no way electromagnetic radiation, that was known at that time anyway, could be falling upon it because the black cardboard box was covering everything. So he concluded this must be a new form of electromagnetic radiations, and he called it X, after the X factor, the unknown, right? You don't know what it is, so call it X. And therefore it got its name as X-rays. So about 6 weeks after he did this experiment, the discovery of X-rays, he got his wife into his lab somehow, and tried to image her hand. And when his wife saw her hand, she famously exclaimed, "I have seen my death." Okay. Well, fortunately today X-rays are associated a lot more with life than death, right? They are used very extensively in medical diagnostics and treatment. They are responsible for saving the lives of millions of people. I mean, millions and more people on this earth, wouldn't have as good a quality of life if not for the existence of X-rays as a technology. In addition to the medical industry, X-rays are also used extensively for failure analysis in other industries such as semiconductor chips. And there are many other applications of X-rays that I'm sure you have heard about or encountered. Quality assurance, forensics, which is crime, trying to, basically CSI, right? Security, right, such as the airport security. Fundamental science, X-rays have been responsible for more than 25 Nobel Prizes in physics, chemistry, and physiology, as well as materials analysis, and the list goes on and on. Okay, so let's see. Right? So with X-rays having so many applications and being so useful, right, it might surprise you to realize that the fundamental mechanism for generating X-rays has not changed since they were discovered 128 years ago, right? Which is surprising when you compare it with other technologies that once depended on the vacuum tubes, such as the computer, for instance. Well, computers were once made up of a whole bunch of vacuum tubes, and they were so huge that they required 2 people to operate, right? And thanks to the semiconductor revolution, we now have computers operating based on very different principles today. Right, the television, right, which was based on cathode ray tubes, right, once again was based on vacuum tubes, right? That's what a cathode ray tube is. Right, thanks to the development of LEDs, LCDs, and plasma, we now have very different televisions, right? Televisions working on very different principles today. The X-ray tube was once based on vacuum tubes, and today it is still based on vacuum tubes, which, raises the question, is there something we can do to make the X-rays, to revolutionize the X-ray landscape? Right, so 10 years ago, we had this very ambitious thought, of being able to do something about X-rays. Of course, we had our reservations, because, maybe it could be possible that the reason why the technology hasn't changed in 128 years was because somehow, coincidentally, it was optimized right from the start. Right, and who are we to think that we could do something about it? But as you know, as human beings, our curiosity and our optimism are unlimited. Right, so we thought, let's have a go anyway. Okay, so how do we start? Well, let's start by asking ourselves, what are the most powerful X-ray sources in the world today? Right, so there are a class of X-ray sources that is much more powerful than the X-ray tube I showed you just now, and which is widely used in industry and medicine today. Okay, so this kind of powerful X-ray source, of which there are very few in the world, is called the free electron laser. It's basically a 2-kilometer long X-ray light bulb, but boy, is it powerful. So what happens in this giant X-ray light bulb is that electrons get accelerated along this linear accelerator stage. It gets accelerated to very high energies, relativistic energies, meaning very close to the speed of light. And then at the end, they are sent through this device called an undulator, which converts the energetic electrons into X-rays. Okay, and this is a picture from one of the first, or I believe the first X-ray free electron laser to be commissioned in the world in 2009 actually, so pretty recent at Stanford. Okay, so here is a schematic diagram of the X-ray generation process in the undulator. You accelerate the electrons, over 1 or 2 kilometers of distance to giga-electron volts of kinetic energy. Then you pass it through this magnetic undulator device. What is the magnetic undulator device? It is very simple. It is nothing more than an alternating series of magnetic dipoles. Why do you want an alternating series of magnetic dipoles? Well, you want to support an alternating magnetic field, because the alternating magnetic field will take your ultra-relativistic electrons and make them wiggle as they traverse the undulator, and the wiggling motion will convert the electron energy into X-ray photons. And looking at this schematic, it basically tells us why it is necessary for this free electron lasers to be so huge. Right, so here is the equation, right? Lambda actually refers to the undulator wavelength, which is 3 centimeters. The X-ray wavelength that we want to target is sub-nanometers. So to go from 3 centimeters to sub-nanometers, you need this gamma factor in the denominator over here to be very large, as you can imagine. In fact, gamma has to be on the order of thousands, which exactly corresponds to giga-electron volts of kinetic energy. And as to the physical significance of gamma, it is nothing but the Lorentz factor from special relativity, if you are familiar with it. If not, just treat it as a normalized quantization of the electron energy. So what did we do? We thought to ourselves, is it possible to make an undulator that is much, much smaller, right? And to do this, we turned to this phenomenon known as surface plasmon polaritons. So specifically, okay, and this is theory, by the way, this is only theory, we thought to ourselves, let's have a dielectric substrate, let's put a layer of graphene on it. Graphene is a van der Waals material, aka a 2-dimensional material, single layer, 2-dimensional sheet of carbon atoms. And what it can do is that it can support these plasmon polaritons. So plasmon polaritons, they are simply surface waves, right? What are surface waves? You guys are familiar with the light bouncing around this room and enabling you to see me and the presentation. These are electromagnetic waves traveling in air and free space. Right? Surface waves are very much like electromagnetic waves traveling in air, except they are confined to travel along the surface. And this gives the surface wave some very unusual properties. One of the properties is that even though the frequency remains the same, at, let's say, visible or infrared wavelengths, frequencies, the wavelength, meaning the spatial periodicity of these electromagnetic waves, can be very small, all the way down to the orders of 10 to 20 nanometers. So what can we do with this 10 to 20 nanometer surface plasmon polariton? We can use it as an undulator whose effective undulator period is 10 to 20 nanometers, and we shoot electrons through it. And the electrons get wiggled, at a very high periodicity. They output X-rays, and what you see here, the figure that you see over here, is basically our ab initio simulation with photon energy on the y-axis and the X-ray emission angle on the x-axis, and you can see that the resulting X-rays have a photon energy as high as about 20 keV, which is actually much higher, or I should say higher than the X-ray photons produced by the free electron laser that you saw on the previous slide. That was only about maybe 4 to 5 keV. This is 20 keV, right? It is very compact, it is chip scale. This is just a 1 micrometer interaction length that we consider. And the output wavelength is relatively directional and also monochromatic, as you can tell from these results. Most importantly of all, we get away by using just 3.7 mega electron volt of electrons. That's about 1,000 times less energetic compared to what we had on the previous slide, where we had to deal with giga electron volts electrons. Meaning that we can now use tabletop electron sources rather than a 1 to 2 kilometer long linear accelerator to drive our X-ray source, right? And for those of you who are quantum physics inclined, this process is actually a second order quantum electrodynamics process, very similar to Compton scattering. And what happens is that the incoming electron, right, the two interacting particles are the graphene plasmon and the incoming electron, and the two outgoing particles are the generated photon, which are your X-rays photons, and the outgoing electrons. So here is the formula that you hopefully remember from the previous slide, except that I've made some important modifications to it, or rather, our concept here has made some important modifications to it. Instead of lambda x being proportional to lambda over gamma square, we have now replaced this lambda by lambda over n, where n is what is called the confinement factor of the plasmon polariton. It turns out that lambda over n has about 10 nanometers. The wavelength is about 10 nanometers, as mentioned, right? And because this number over there is very small, in order to get a similar output wavelength of about, sub-nanometers, you now need a much smaller gamma, a much smaller electron energy, and that's how we get away with a more compact electron source. Okay, so this is a very interesting idea. I emphasize once again, this is just theory and ab initio numerical simulations. Right? We were very eager to perform the experiment, and I'll tell you after this slide, what's going on with the experiments. Okay, so let's have a comparison with the state of the art. Right? We find that our polaritonic undulator concept actually falls nicely in between the brightnesses that can be generated with the conventional X-ray tube and the brightnesses we can get with our synchrotron sources. So a synchrotron is like a free electron laser, except instead of being linear, people have wound it around, curved it around in a circle. Okay, it is pretty large, not kilometers long, but it would definitely be a stadium sized, right? And of course, they have high intensities, much higher than the X-ray tube, and we find a very nice feature of this polaritonic undulator is that with relatively modest currents, in fact just 1 microampere of current, we can actually already achieve brightnesses that fill the gap between X-ray tubes and synchrotrons. At the same time, they are as compact as X-ray tubes, and they also have a very important feature in the sense that X-ray tubes are not tunable, meaning the output X-ray wavelength is fixed. You cannot change it. It is dependent on material properties. Right? On the other hand, synchrotrons are tunable. You can actually vary the output X-ray wavelength continuously by changing the electron energy. And because our X-ray generation mechanism is free electron based, it turns out it is tunable as well. We can vary the output X-rays the frequency generated by changing the electron kinetic energy. And not only that, we can further enhance this value of brightness using things like pre-bunched electrons, which is to convert the electron distribution into nano bunches, which would make the radiation more coherent and more intense. Right, we can consider higher currents outside the microscope. So far, we have just considered 1 microampere of current. Right, we could go to 1 milliampere or maybe even 1 ampere with special vacuum electronics. Right, we could think of higher field strengths. So far, we have been considering graphene plasmon polariton fields of about 1 gigavolt per meter. Right, if we are able to push that by a factor of 10, then we expect the X-rays to scale up even further. I think that would correspond to about a factor of 100. And a longer interaction length would help as well. So far, we are only considering an interaction length of 1 micrometer, right? So all this was very exciting theory, and it didn't, right? And this was back in 2015, 2016. We were very excited about this theory, and we were very excited about converting it to an experiment. And it didn't happen. The experiments didn't happen for one very specific reason. Basically, we needed a very high plasmon polariton field for it to be realized, right? We need about 1 gigavolt per meter of electric field, and the people who have been generating plasmon polaritons, they have been doing excellent work, and also developing excellent applications. But the main focus or based on my observations anyway, the main focus has not been on the field strength. So we are waiting, to see if the community can scale up the field strength one day, and this theory is waiting in the shadows, for that day to come. Okay, so that was the challenge, that actually kept us from experimentally realizing this, even though we like the idea a lot. And in the meantime, what do you do when you're waiting to experimentally realize an existing theoretical idea? You come up with more theoretical ideas, right? So later on, right, shortly after that, we thought to ourselves, why stop at a flat sheet of graphene? Why do we not move on to something more creative, such as metal surfaces? Right, so what we showed in this work was basically that you could create metal surfaces that could shape the plasmon polaritons, and in turn the shape of the plasmon polaritons would control the output spatial profile of the emitted X-rays. So that's pretty cool because you're shaping your X-rays at the source. Right now, in order to shape your X-rays, you need to have external X-ray optics, which always introduces additional losses and distortions. Here you can shape it directly at your source, which is pretty nice. And then we also thought about how to scale up the X-ray source even further. Instead of having a single layer of plasmonic material, we could have multiple layers of plasmonic materials and turn it into a multi-layer material, aka a plasmonic metamaterial. And instead of having the electrons fly over the metal surface, we could have it fly into the metal material to generate lots more X-rays, because we have lots more electrons now, since we can take advantage of the larger volume of the material, right? And how about not talking about plasmon polaritons at all, but relying on the magnetic undulator, but now we design magnetic domains to be alternating on the order of nanometers rather than centimeters as is currently used in the undulators, right? So here's the idea of magnetic nano undulators. And then finally, here is an approach that's very interesting, you know, for its I would say it's interesting mainly because of fundamental physics, but if you could turn this into an application, this is pretty cool as well. Basically, we started to ask ourselves, do we even need an external driving field? You know, and this X-ray from Casimir forces is basically an idea that removes the input laser power completely. We do not need an external laser now to excite our plasmon polaritons. Where do we get our plasmon polaritons from? Directly from vacuum fluctuations. So it turns out that the vacuum fluctuations that exist near plasmonic surfaces, right, they assume the form of plasmonic modes, and they are sometimes extremely confined, such that we find that if we were to shoot the electron close enough to a plasmonic material, the vacuum fluctuations can actually wiggle the electrons, you know, with a strength that's comparable to a 1 Tesla magnetic undulator in a synchrotron source. So that's pretty amazing. How can vacuum noise, you know, be comparable to a 1 Tesla magnet in a synchrotron source? But that's the case. What's the catch? The catch is the electron needs to be really, really close to the material, right? And you can understand this phenomenon from the context of Casimir forces. So for those of you who are physics inclined, you may remember that the Casimir force is this mysterious attractive force that occurs when you put two metal plates very close together. So here you can think of the first metal plate as being the sheet of electrons flying above the plasmonic material, the metal, and a second metal plate as being this plasmonic material itself. And in between, you know, you are experiencing basically an attractive force that is causing the electrons to wiggle. And the wiggling of the electrons produces emission. Actually, it's a very broadband emission, but there is substantial emission in the X-ray regime. So these are our theoretical ideas. Okay, and well, you know, we wanted very much to find an idea that we could experimentally realize right away. And it turns out that in studying all this theory, we managed to find one theoretical idea that allowed us to implement a small tunable X-ray source. So here is how we did it. So we did it using van der Waals materials, but not quite in the way that I described just now. Just now we used the surface plasmon polaritons of van der Waals materials. This X-ray mechanism that we discovered and which I want to share with you right now has to do with using the periodicity of atoms in crystalline van der Waals materials. And here is how it works. First of all, we have a stack of van der Waals materials, of van der Waals layers, so you can think of each of these, or rather you can understand each of these layers as single atom layers, right, of two-dimensional materials. And we are shooting electrons through these two-dimensional materials, and X-rays are being generated via two mechanisms. One of the mechanisms is called parametric X-ray radiation. How does it work? You know, basically the electrons that pass through these two-dimensional materials, right, they basically see these two-dimensional material layers as nanometer gratings, nanoscale gratings. And these electrons excite dipoles in these nanoscale layers, and these dipoles oscillate and generate radiation, and that is called parametric X-ray radiation. For those of you who are familiar with this phenomenon called the Smith-Purcell effect, this is simply the Smith-Purcell effect at the atomic scale. The second method of X-ray generation has to do with, is very closely related to the undulator effect. The electron is actually being wiggled back and forth by the electrostatic field in the atoms, and that causes it to generate radiation in the form of coherent Bremsstrahlung. And it so happens that these two effects, they are actually both part of the same X-ray generation mechanism, you could say, in a sense. Why? Because this is the first order effect, this is the first order mechanism of X-ray radiation, this is a second order term in the X-ray generation mechanism, and they both happen to generate X-rays that peak exactly at the same wavelength. Okay, And here again is the familiar equation, right, that you have seen a few times before already. We are using once again the undulated radiation, and the way this allows us to get away with very low energy electrons is because our lambda now is on the atomic scale. Specifically, we are exploiting the nanometer scale periodicity inherent in these nanometer scale stacked layers. So here is a similar cartoon of our experimental scheme. This diagram basically emphasizes the two parameters that we can vary in order to vary our output X-ray wavelength. One is the electron energy, and the second is stator tilt, which is the tilt angle of the crystal. And here are our experimental results. On the y-axis it's counts, and on the x-axis is photon energy. First of all, we are varying the tilt angle of the crystal from 0 degrees, 10 degrees, all the way to 25 degrees. And we see that theoretical predictions, which is the solid curve, match experimental observations, which are the dots, pretty well, right? And the dotted lines is basically the X-ray peaks predicted by our theory. And in this second plot over here, we are doing exactly the same thing, except we are now keeping the tilt angle fixed, and we are varying electron kinetic energy. So as you see, as we vary the electron kinetic energy from 60 kilo electron volts all the way to 300 kilo electron volts, the output X-ray peak shifts accordingly. And once again, there is a reasonably good match between theory and experiment, right? So basically, this panel tells you, the takeaway from this panel is that you can continuously and precisely tune the output X-ray wavelength by varying the tilt angle of the van der Waals material. And in this second panel, it tells you that you can continuously and precisely vary the output X-ray wavelength by varying the electron kinetic energy. So two methods of tuning this, which you definitely do not have in conventional X-ray sources, because those X-ray peaks are fixed based on the properties of your material. Right, and this is just to emphasize that the X-ray peaks we measure are actually very narrow band. The reason why they appear to be so broad band over here is only because of the resolution of our X-ray detector, which is on the order of 100 electron volts. So we did our experiment in the FACS facility, the Facility for Analysis, Characterization, Testing and Simulation at NTU. Here is one of the instruments that we use, a transmission electron microscope. Here is a TEM image of the material, and this is a diffraction pattern which tells us that the material has the very important crystalline properties that we are using to generate our X-rays. Right? And so far I've talked about two mechanisms of tunability. The first one has to do with tunability via tilt angle over here. Right? I've also talked about tunability via electron energy, which I represent by drawing two graphs, one of which is for electron energies at 120 keV, the second of which is for electron energies at 200 keV. There is a third degree of freedom, right, that I haven't talked about, making this an extremely versatile X-ray source, and that is tunability via atomic composition. Right? Van der Waals materials are extremely versatile class of quantum materials. You can change the cation ion or change the anion to vary the interlayer spacing very precisely. You can even come up with your own customized Van der Waals heterostructure material. This is something that the material scientists are currently very excited about. And an application we have for this exciting new class of material is to use it, as a way of generating very versatile X-rays, shaped X-rays, X-rays that we have many degrees of freedom to control. Okay, so far, the status of this is that, we have published our papers, we have filed our patents, we even got a technological evaluation license purchased by a local a local company in computed X-ray tomography with whom we are collaborating to create the first prototype for X-ray imaging using this technology. And while we are waiting for this first prototype to be realized, I'm very pleased to report, right, that we actually already have an application, right? We have actually already demonstrated an application of this X-ray generation mechanism, right? And I put the word application in inverted commas because it's not an application in a commercial sense. It's an application in the sense that this X-ray generation mechanism actually allowed us to prove this theory known as the quantum recoil theory, which was postulated 83 years ago in 1940, but which hasn't been proven until now. And what exactly is this quantum recoil theory? Well, you know, the Russian physicist and Nobel laureate Vitaly Ginzburg came up with it in 1940 to say that when we study photon emission from electrons, that is to say when light is emitted by electrons, right, the electrons do not remain undeflected as predicted by classical theory, right? Classical theory predicts that the electron doesn't get deflected. Why? Because classical theory treats radiation as waves. They do not treat radiation as particles with energy and momentum that it can exchange with other particles. It treats it as a wave which does not deflect the particle, the electron, as it moves along. But Ginzburg said, well, based on the fact that the photon is a particle, surely its emission must cause the electron trajectory to be deflected, to be affected in some way. And in turn, the deflection of the electron trajectory should have a back reaction on the photon energy, and the change in photon energy should have a back reaction on the electron trajectory, and back and forth. You know, it's basically a set of simultaneous equations for energy and momentum conservation. Right? You solve these simultaneous equations at once, and you will find, surprisingly, that you have a set of emitted frequencies that are very different from the emitted frequencies predicted from classical theory. How different? Right? Classical theory predicts that the emitted frequencies will be integer multiples of a certain harmonic. Quantum theory, quantum recoil theory, predicts that the output photon energies are no longer integer multiples of some fundamental harmonic, and not only that, they can be substantially shifted from the classical predictions. So I put up this slide, you know, just to highlight that Smith-Purcell and Cherenkov radiation, which are examples of spontaneous emission in free electron radiation, these are not old topics either. These are topics that have been studied for a very long time. They are actively studied. There was a Nature paper in 2023 from MIT, you know, in fact, my close collaborators, on the Smith-Purcell effect, Smith-Purcell emission using photonic flat bands. Right, and this is a very actively studied field, but nobody has ever managed to access a regime where quantum recoil was significant enough to be observed in these free electron spontaneous emission mechanisms. Right, so what we managed to show is that with our X-ray mechanism, we have finally managed to penetrate a regime where we could demonstrate quantum recoil, where quantum recoil, you know, shows up very significantly and actually affects the X-ray technology that we are trying to design. Right, and you may be asking, how did you manage to access this regime? Well, you know, one thing is we are working in the X-ray regime, which most of the people previously were not looking at. They were looking mainly at, you know, the optical regime, infrared, you know, maybe terahertz, maybe a little bit of ultraviolet, but nothing as energetic as the X-ray regime. And secondly, we are using a periodic grating which is nanometer scale. Right? Most people, when they try to demonstrate Smith-Purcell radiation, they would be using a grating that is, you know, let's say hundreds of nanometers typically, you know, and sometimes even larger. But by using a crystalline material, we are automatically using periodicities that's order of nanometer scales. And apparently this combination of parameters brings us into a regime where quantum recoil is very significant. And exactly how significant, you know, let me show it to you in a quantified way later on. So here's our experiment where we demonstrated quantum recoil. What did we do? We basically conducted exactly the same X-ray generation experiment that I showed you before. The only significant difference is that instead of measuring the second harmonic, right, in this case we actually have the crystalline properties actually only give us even harmonics, not odd harmonics. So instead of just measuring the lowest harmonic, which is the second harmonic, we measure two harmonics, the second harmonic and the fourth harmonic. Why do we want to measure two harmonics? Because I want to take 2 times the second harmonic minus the fourth harmonic. Why am I interested in this difference? Right? Because if you remember classical theory just now, it tells us that the radiation emitted is an integer multiple of some fundamental harmonic. Meaning if I take 2 omega 2 minus omega 4, I expect to get exactly 0 for classical predictions. And indeed, if you were to look at the classical theory predictions, these cyan lines, they are approximately 0. Why not exactly 0? Because we have done very realistic simulations. We have used Monte Carlo simulations to capture external scattering effects. And that explains the deviation of from 0. And we have run the same simulations for the quantum recoil theory to get this set of green theoretical predictions. And you can see that the experiments which are in red agree much better with the green quantum theory compared to the cyan classical theory. And this allows us to conclude that we're finally accessed a regime where quantum recoil is observable and significant. Okay, so let me actually take one of these points, let's say this point 11.7 keV, and let me zoom in into this point to show you the actual spectrum that we measure in our experiment. Right, the y-axis is the X-ray counts, the x-axis is the photon energy, and the quantum theory is once again in green, the classical theory is in blue, the experiments are the red dots, and you can see once again the good agreement of experiment with the quantum theory, right, which is significantly deviates from classical theory. Right, I say significant, right, but you know, you might say, well, not too significant, the photon energy shift is 3%, right, it is observable, but maybe, you know, you're hoping for like a huge photon energy shift. I will show you in maybe just one slide, you know, that this is actually possible, okay, and yeah, you know, to explain why our photon energy shift is so small is because of the experimental constraints we are working in. Specifically, our X-ray detector is fixed at a certain observation angle. In order to access a regime where the quantum recoil is very huge, actually all we need to do is to change the angle of our observation of our X-ray detector, which hopefully we can do by the end of this year when we get our customized setup. So here is a graph of the quantum recoil, the shift in the photon energy, h bar delta omega. Delta omega would be the difference between the classical photon energy and the quantum photon energy, aka the actual photon energy, right? And this plot, okay, it is theory. This plot was generated for a classical X-ray photon energy of 300 eV. And you know, check this out, right? In this regime, transmission electron microscope, meaning we can do it on the tabletop scale right here in NTU, right? Technically, right? We can actually access a regime of quantum recoil that is so large that the classically predicted X-ray photon is actually emitted as a very low energy photon, right? In fact, in this regime, it is predicted that no photon is emitted at all. And if you go to this regime where it is almost 300 eV, it's basically telling us that your photons emitted are as low as, you know, terahertz, microwave, even radio wave. Right, so if you're not careful with your theory, right, if you're not careful setting up your experiment, you might end up actually predicting X-rays, but you end up getting microwaves or infrared photons, you know, right, which is amazing. You know, this is a quantum effect taking place at room temperature, you know, in the presence of all the other scattering mechanisms. It's very noisy and it's manifesting very strongly. It is a quantum effect because there is a very strong h-bar dependence in the theory. Right, if you think of other quantum effects like the Lamb shift, you know, that's just a very small percentage shift, you know, yet it's very significant. And a lot of other quantum experiments, you need to go to very low temperatures, you know, like near 0 kelvins in order to observe it. But over here, in this case, here is a quantum phenomenon that shows up boldly, proudly, you know, unabashedly in our everyday experiment, so to speak. So based on this, we were actually quite impressed, you know, that quantum physics is actually showing up, manifesting itself in such a, you know, unavoidable way, right? And it also has very important implications for the X-ray technology we are trying to develop, which means that in order to develop a precisely tunable X-ray source, quantum effects are definitely not avoidable, right? So the advantage of our scheme is that we can do this, we can generate tunable X-rays on a very small, on a chip scale, on a tabletop scale. But the disadvantage, well, I wouldn't call it a disadvantage, you know, but the part we need to be very careful about is that we cannot ignore quantum effects. Okay, so, you know, here is an outlook about what we can do with this platform, besides using it to generate an X-ray imaging system, right? We thought about using it for even more fundamental physics, namely a compact platform for studying this problem called radiation reaction. Okay, so radiation reaction is, by the opinion of many physicists today, the last unsolved problem in classical physics. Actually, I'm of a slightly different opinion. I have in mind a few other problems that classical physics haven't tackled yet, you know, but maybe it's because they have some quantum elements in them. Okay, but basically the radiation reaction problem has to do with the Lorentz force equation, right? What is the Lorentz force equation, right? If you recall from your, let's say, you know, freshman physics, right? The force experienced by an electron is given by its charge multiplied by the electric field plus V cross B. right? The Lorentz force equation. It tells us how electromagnetic fields exert a force on charged particles. Well, guess what? The equations you have been learning, you know, and which I've been teaching because I was teaching the E1102. I've been teaching E1102 this semester, right? The equations I've been teaching is actually incomplete. You know, it is incomplete because it's missing this last term over here called the radiation reaction term. Right, think about it. When an electron moves in an electromagnetic field, is it not accelerating? And if it is accelerating, shouldn't it be losing energy? Shouldn't it be experiencing a force because it is losing energy and being deflected in its trajectory thanks to the emission of photons? Yes, indeed, it should be, you know. So that's a self-force, right? That's a self-force that is not taken into account. The Lorentz force equation tells us how external fields affect the charged particle, but it doesn't tell us how the charged particle in moving around and accelerating is affecting itself through the process of electromagnetic radiation. Right, so this is actually a problem that's been tackled by many famous scientists, you know, and I'm very sad to say that none of them have actually got to a point where they can convincingly solve the problem, including Lorentz, Abraham, okay, yeah, I didn't put Abraham's name here, Dirac. The Lorentz-Abraham-Dirac formulation is actually one of the oldest formulations for radiation reaction, and then there is also Landau-Lifshitz as well. Right, and as recently as 2022, right, scientists are saying radiation reaction is the oldest, still unsolved problem in electrodynamics. But this is where it gets very interesting for us. Because what we have found in our platform is that our electrons are actually experiencing substantial recoil at room temperature, you know, on a tabletop scale. So it's very interesting to explore whether our tabletop mechanism could be some sort of platform to study quantum electron-photon interactions such as this radiation reaction problem. Okay, so much for the particle nature of light. Okay, the particle nature, right? So this radiation reaction has to do with the particle nature of light. The fact that the particle nature of light means light possesses energy and momentum. Because it possesses energy and momentum, it's going to experience exchange of energy and momentum with the electron from which it is emitting, and therefore lead to a shift of its radiation wavelength from the classically predicted values. Now let me talk about another aspect of quantum physics that will be affecting our radiation problem. And now I'm going to talk about the wave nature of electrons. Right? There are two sides of quantum mechanics. One is the particle nature of light. The other is the wave nature of electrons. Before the 1900s, everyone believed that light is a wave, electrons is a particle, the electrons are particles, and that's it. Right? But now we know that electrons, they are actually not strictly speaking particles. They have a probability distribution that evolves, you know, very much like a wave. And the question that we are asking ourselves here is that can we change the radiation properties of a free electron by shaping its electron wave function? Okay, I will say that again. Okay, the electron can be represented by a wave function which is associated with its probability distribution. By changing this probability distribution, can I shape the output radiation of the electron? Right? An example of free electron radiation, spontaneous emission, would be Bremsstrahlung. Basically, we have an electron encountering an atom, let's say a carbon atom, and because the electron is deflected by the nucleus in the carbon atom, it produces radiation, right? So let me ask you, can I change the wave function of the electron and somehow affect the output photon? Intuitively, the answer we expect is no. Okay, why not? Right, this has to do with the interpretation of the wave function, right? Early on, when Erwin Schrödinger first came out with the Schrödinger equation, he said the probability distribution represents a charge distribution. But later on, physicists pointed out, they realized that it is wrong. It is not a charge distribution, it's a probability distribution. It is sort of like saying, you know, it's sort of like me telling you, I'm going to Suntec City this weekend, you know, so you know that my probability distribution is somewhere around Suntec City, right? But the fact is, no matter what my probability distribution, you can change my probability distribution by telling me not to go to this place, not to go to this shop, not to go to this shop, please stay within this tower in Suntec City. You can change my probability distribution, but you will not be changing me, you know. Even if you change my probability distribution, you know, in the end, I'm still a human being, you know, walking around in the same way, right? And in the very same way, even if we were to change the wave function of the electron, as Feynman says, the electron is either here, there, or somewhere else, but wherever it is a point charge. Right? So if you're not changing the electron, why would the radiation from the electron change just because you are changing its wave function. Remember, the wave function is only telling you where the electron is located. Right? You're not really changing the electron, so why would we expect shaping the wave function to change the radiation property of the electron? So what we did was we turned to quantum electrodynamics to try to verify our intuition, and surprisingly we found out there is a regime where the output radiation profile of the electron radiation can be made to change substantially. Right? So this is quantum electrodynamics. We are calculating basically the cross-section of the Bremsstrahlung problem, which is represented here. Here is a plot of the photon energy of photon energy on the y-axis, angle of emission on the x-axis. I'm plotting basically the differential cross-section, which is proportional to the intensity of the Bremsstrahlung radiation. You can see that it has an off-peak distribution. Okay, if I were to add up two processes, if let's say I shape my electron so that it doesn't have just one momentum state, it has two momentum states, right? QED tells me I just need to add up the two cross sections, and I'll end up getting this, which is not very much change from the original distribution. But if I were to choose a very special state 1 and state 2 such that the output of both processes are exactly the same, then a very surprising thing happens in quantum electrodynamics. This surprising thing that happens is a phenomenon known as quantum interference. The two processes will interfere, and suddenly, instead of solving this problem a squared plus b squared, you are solving a plus b squared, where there is a cross term 2 times ab that you cannot ignore. And this cross term is so substantial that it can allow you to reshape your radiation from something that's quite non-directional to something that's pretty directional. And if you were to use this directivity, which is a figure of merit used by electrical engineers in antenna theory, you can see that we enhance it by more than a factor of 10. And we can do this not just for the problem of Bremsstrahlung, we can do this for undulators as well. Right, so if I were to send the electron through the magnetic field, once again I expect to have output radiation thanks to this wiggling process that I've described. Right, if I were to look at the case for one state, I notice first of all an undulator peak, because here I'm choosing a very short undulator, just like let's say a 10 period undulator, very short undulator. So I have a nice peak over here, but I also have a very huge background over here, right, which I probably don't want. I want this peak and I don't want this background, for example. If I were to have two state, and I use the word incoherent to mean that the overall cross section is simply the sum of the individual constituent cross sections, I will end up with pretty much the same output cross section profile. However, if I were to choose my input conditions very carefully so that I have quantum interference between the two processes, I end up with a constructive interference in this peak. Well, actually, I don't have a constructive interference. I have this peak being pretty much the same differential cross-section that it was before, but now notice that my background has been substantially eliminated. Why? Because there is a cross term appearing thanks to my quantum interference that destructively interferes. It basically causes, the background in the two quantum processes in question destructively interfere with one another, and now suddenly I have a very pure signal, right? I have a peak and I do not have background radiation. Right, so that's something interesting. Remember that we are talking about the quantum wave function of just one electron. So this is not quite the same as shaping your radiation like using a TV antenna, right? That's shaping radiation using multiple charges. Here we are shaping the wave function of one electron. And just by controlling the wave function of one electron, we can increase the directivity by 10 times. We can suppress the background radiation substantially. So there's a lot we can do, using with quantum engineering of the electron wave function. So here is the overview of the roadmap that we have come up with for what we can do, what lies ahead. Right, first of all, we are interested in generating unshaped electron wave packets for the purposes of shaping them. And shaping them, actually, we can use a bunch of mechanisms. We can use here a biprism, right, static fields. We can use RF cavities. This is actually an RF cavity that could be used in a linear accelerator, but which we can also use to shape electrons. We can use light, optical light, infrared light, ultraviolet light to modulate my electron bunches and shape them in both space and time. We can also use phase masks and many other methods. Once we have shaped electrons, we can use these shaped electrons to interact with the X-ray mechanisms that we have developed, right, including plasmonic structures, which is, as I mentioned, theoretical for now, but hopefully one day we can push it to experiments as well, right, metamaterials, quantum materials, and so on. And what do we get out of this? Right, we get photons and electrons at a whole range of energies. We get electrons, of course, the output electrons. We get X-ray photons. We can also get optical and terahertz photons if we can engineer 2 photon emission processes, which is what is happening for the case of the X-ray emission from Casimir forces. And the best part about this is that the output particles, they are all entangled due to energy momentum conservation. So using this entanglement, if you ignore the entanglement, you can use the X-ray photons for things like hyperspectral X-ray imaging, which is something that we hope to do a proof of concept experiment of, hopefully by the end of this year. Right? By exploiting the entanglement, you can do things like heralded generation of single photons in the X-ray regime for quantum information applications. And you can also do things like coincidence measurements, which is basically you only measure your X-ray photon if you detect an electron at the same time that satisfies energy momentum conservation. And this has been shown by researchers to substantially suppress background noise. So basically you can exploit the entanglement to access advanced imaging and more precise imaging modalities. Right? So in conclusion, okay, I've talked about how we are working towards a compact tunable source of X-rays. I've talked about how we have used our X-ray source as a platform for quantum electron-photon interaction, specifically for the demonstration of quantum recoil. I've talked about how we can control and enhance radiation processes by shaping the single electron wave function, right? So a very, very distant vision would be to not only control the location and the distributions of the classical electrons as point charges, but also to shape the electrons precisely. And actually that's something we are studying theoretically as well, because nobody has even got around to studying it, to our best knowledge at this point, right? And finally, I talked about this roadmap on nanophotonic enhanced X-ray sources. Okay, so yeah, finally, I would like to acknowledge, my research team here at NTU and also around the world. Especially, I would like to acknowledge 3 of the people who have worked very hard on many of the achievements that I showed you on this slide. My postdoc Sun Chao, my PhD student Nikhil, and the postdoc Rui Huan, who is from Professor Liu Zheng's group. And I want to say that I currently have PhD scholarships, so if anyone is interested in working on a PhD in these topics or know of someone who is, please spread the word, okay, or please drop me an email. And yeah, that's the end of my talk. Thank you very much. Questions? Yes.
Okay, thank you very much for the interesting talk. I will moderate today the Q&A session. First of all, I would like to start asking you a question. I would like to ask you, when did you start your research in quantum recoil, and how did you get attracted by this field specifically?
Yeah, okay, so how did I start my research in quantum recoil? Well, first of all, we didn't start thinking about quantum recoil, right? We actually started working on this tunable X-ray generation problem. We were very interested in finding a way of generating X-rays, tunable X-rays. And what we found, surprisingly, is that classical theory couldn't match our tunable X-ray experimental results. Right? So we actually went to look at quantum theory, and we found out that quantum theory could provide actually a better match. It was only slightly better, but this made us think, could this be the first experimental demonstration of quantum theory? And after a lot of very hard work, especially on the part of my postdoc Sun Chao, yeah, we managed to find actually a regime where the quantum effect actually manifests substantially. Yeah.
Okay, thanks. If anybody has some question, you can raise your hand.
So I have 2 questions. The first one is, so there have been efforts to use the inverse pinhole effect to make terahertz emitters. Has something like that been considered for X-rays?
So sorry, what was that?
So there have been efforts to make terahertz emitters using in the inverse pinhole effect. So you have a ferromagnetic material that generates a spin current, and then the inverse pinhole effect makes a unidirectional charge current.
The inverse pinhole effect. Yeah, we have been very interested in the idea of using magnetic fields, and skyrmions for the purposes of generating X-rays. The fact is that as long as you have some form of alternating electromagnetic field, right, and you interact that with your electrons, you have a chance of doing this relativistic Doppler upshift, which is that the radiation generated by your electrons basically becomes a lot, you basically access a much higher frequency regime with your electrons. Another way to think about it is the electron is actually a very, very effective nonlinear medium. So yeah, we could think about these effects, right, magnetic effects. I guess you could say that there's actually a lot of theory ideas in this field, that actually remain to be explored and published. So if anyone has any interesting ideas that you'd like to talk about, I'm most happy to discuss that as well. Yeah.
And secondly, for the work that you showed about shaping electron wave function and altering the emitted photon, so how easy is it experimentally to say put one electron in a superposition of states? Because if you have many electrons, probably the scattering might destroy it.
Right, that's a good question. How easy is it to put an electron in a superposition of states? Well, I wouldn't say it's extremely easy, but people have definitely found way to shape electrons. So one way will be using a biprism, which is like a charged rod, and basically you have a single electron state coming down, and it basically gets deflected into two cross beams. So that would be a simple way of shaping it, taking a one-state electron and making a two-state electron. People have been coming up with more complex ways of shaping the electrons as well. It's a very active field of research. I would not say it's quite a mature technology yet, but hopefully we get there. Yeah, Matthew.
So with regards to the graphene plasma, which you said there was a limit on the currently achievable powers.
Mm-hmm.
What is limiting that? Is it literally melting? And how far are you off getting to the intensity you need?
Yeah, okay, I like that question a lot. So the question was, I mentioned that there is a current limit on the existing electric field of plasma polaritons. Okay, so I would say, in fact, I would not call it a limit, right? What I meant is that when people study these plasma polaritons, their focus, of course for very good reasons, their focus has not been on the intensity, right? I'm not aware, but feel free to let me know if anyone is aware. I'm not aware of efforts of achieving very intense plasma polaritons, or at least not to the levels that we are interested in, which is on the order of 1 gigavolts per meter. So 1 gigavolts per meter, based on our calculations, would still be a level of electromagnetic field that would not cause damage to the dielectric material and to the graphene as well. Yeah, so it is known that at these optical frequencies, materials typically have a much higher damage threshold. Yeah, so we don't expect that to cause damage, but we are also not aware of any plasma polariton work that comes anywhere close to those intensity levels. Yeah, and as to why, I guess it's just easier to work with lower intensities. You do not need a laser of such high power and so on. Yeah. Yeah. Yes.
Hello, Professor. Thank you for your fascinating seminar. I have a question about how do you choose the
Okay, so very good question. So there are two questions here. One is, how do we choose the van der Waals material? Well, depending on applications, depending on what output wavelength you want to access. So when you choose your van der Waals materials, what gets fixed is the interlayer spacing. Sometimes even that doesn't get fixed because there's ways to dynamically control the interlayer spacing of some van der Waals materials. So but that will be how you want to choose it. And bear in mind that even after you choose your material, things are not completely fixed. You can still tune your electron energy and tune your tilt angle and so on in order to vary the output wavelength. Yeah, but basically, all van der Waals materials will be good candidates. Okay, let me add in another consideration. You also want a van der Waals material that can give you high intensity, if that's what you're interested in. So typically, if you have van der Waals materials with heavier elements such as tungsten in them, that would tend to give you more intense radiation. Right, and the second question would be regarding the damage. Right, if we shoot the electrons into the material, would there be damage? Right, so this is actually something that we have calculated, and it turns out that it can go up to as high as 1 milliampere or even 10 milliamperes and not damage the material. But this is not something we can experimentally access in our TEMs, because those are only 1 to at most 100 nanoamperes. But we have done thermal simulations, and we're currently working with CT Metrics to build this imaging prototype, which will be using high currents. So we expect that you know, we can actually tolerate quite substantial currents. And yes, we do take into consideration scattering effects in our simulations as well. Yeah.
Will the electron penetrate? Should it penetrate deep enough to generate X-ray?
Yeah. Yeah. Yes. Yeah, it does penetrate deep enough to generate X-rays. So the X-rays generator is about 100 to 1,000 times, and this is unoptimized compared to the background Bremsstrahlung radiation. Yeah, and if you want even deeper penetration, you can basically use a more energetic electron, which we haven't even explored yet, because so far we have been limited to 200 keV electrons.
Will it go that deep without getting scattered?
Well, yeah, there's definitely. So his question is, will it go that? What do you mean by that deep? He said, will it go that deep before it gets scattered? What do you mean by that deep?
Sorry, I think you mean that you need the electron to go deep inside the crystal to generate enough X-ray, right? So will it get scattered on the?
The answer is that yes, it will get scattered, but even after it gets scattered, it can still generate X-rays. Yeah, so it will.
Because its initial energy is high enough to support it to go.
Right.
Okay,
Yeah.
thank you.
Yeah, we can even go as low as a few kilo electron volts, and we still can observe this X-ray emission.
Okay, thank you.
Yes, Chris.
In our electron microscope, we make use of the Lorentz force. We make use of the Lorentz force and strong magnetic field in order to bend the electrons. But you've just told me that the equation for the Lorentz force has got an extra term, which will cause some extra energy loss.
Right.
Which means that now, when my electrons are bent, they won't interfere with each other, and therefore my microscope doesn't work. What do I do?
Well, I don't think the radiation reaction force would produce such a big effect, you know, as to keep the electron microscope from working. If it was, you know, I'm sure the engineers would have encountered lots of problems building the microscope. So I think the best explanation there is probably that we are fortunately in a regime where radiation reaction does not have a very strong contribution.
It would be interesting to know about this, because there are problems in interpreting the contrast in image of microscopes, and maybe there's something that has an effect here.
Right, it is true. And by the way, you know, this bending of the electrons is exactly the reason why we need to use a linear accelerator if we want to get the electrons up to a very high energy. Right. So the question, the natural question that people will wonder about is, why don't we just keep using circular structures which are more compact to accelerate the electrons? And that's because the circular acceleration causes a lot of energy loss via radiation, and that's not sustainable. Yeah.
Any other question from the public?
Thank you for the talk. I want to ask, how far is this from commercialization?
Yeah, so how far is it is basically that a company has purchased our technological evaluation license. We are working with the company to build the first prototype. And recently we got invited over to AMD to give a talk about this, and I'm pretty interested as well. So there are a lot of engineering challenges to overcome, no doubt about that, right? But hopefully we get our first prototype by the end of this year.
Do you think the application can be in medical imaging or more in a research setup?
I would say yeah, that's a good question. So I would say right off the start, you know, this kind of device or prototype, you know, would be more useful for imaging biological cells, right, and perhaps small devices such as semiconductor chips. For medical imaging, that also remains a possibility, but what we need to do then is to scale up the X-ray photon energy up into the very, very hard X-ray regime. But that's pretty much it.
What would be the advantage to comparing with the X-ray tubes?
Or what would be the advantage compared to the X-ray tubes? That's the whole point of the research. One of the biggest advantage would be the tunability. Basically, instead of having just fixed wavelengths to work with, you know, or averaging over all the wavelengths you can access from your X-ray tube, you now have an X-ray peak that you can tune to wherever you want it to be. And this is extremely important because different materials, they respond differently to different X-ray frequencies. your absorption contrast is actually a very, very strong function of frequency. If you go and look up your material X-ray absorption curves, right, they are very strong function of frequency, but this is completely not exploited. I wouldn't say completely not exploited, but this is minimally exploited in today's X-ray imaging because they are either using the fixed characteristic line peaks or they are averaging over all wavelengths. Now we have a way to actually shift the wavelength peak to wherever we want it to be. So if you consider two elements, aluminum and silicon, were side by side on the periodic table, their absorption profiles actually almost overlap each other except for a very narrow region between 1.5 keV and 2 keV, which is the absorption edges. There's no way we can use a conventional X-ray source to access an X-ray peak, you know, exactly in that regime. Right, but with our continuously tunable X-ray source, we can actually go there precisely.
I see, that's really nice.
Yeah.
And how about cost-wise?
Yeah, cost-wise, we don't expect it. Well, I mean, cost-wise is a good question. You know, it depends on what needs to be done to overcome, you know, engineering challenges, which we as fundamental researchers sometimes have a hard time foreseeing. Right, but overall speaking, I wouldn't expect it to differ much from the conventional X-ray tube because essentially it's the same setup. X-rays shooting at, you know, an anode material. Yeah, the difference is that now we're exploiting a different X-ray mechanism.
I see. Thank you.
Thanks. Yeah.
Yes. So I think the electron transfer along the c-axis, is there any thickness dependency of this phenomena?
Is there any, sorry?
Thickness dependency, the thickness.
Right, thickness dependence. Okay, so basically the longer these electrons travel, the deeper they travel, the more radiation they produce, and it scales as the interaction length square if they are not deflected. Yeah.
Have you considered the in-plane, the AB plane?
Have we considered the in-plane? What do you mean by that?
So now the geometry, the electron transfer along the c-axis.
Yeah.
How about along the AB plane?
Oh yeah, that's a good question. So yes, you know, you could indeed consider the electrons going this way as well. Yeah, that's an experiment we're trying to do right now. Yeah, because there's also periodicity in this direction, right, which is actually smaller periodicity. And that would allow us to access a different regime of wavelengths. Yeah.
Any other question? Sure. Since we have discussed the possible commercialization of this research, would you like to share also some advices for students that would like to pursue an academic career after graduation?
Academic, right, advice. Well, you know, yeah, I mean, this is a good topic, you know. I mean, I was talking to some students, undergraduate students, you know, and I find that not all undergraduate students have the right perception of a PhD. Right, and for those academicians among us, you know, including those who are already pursuing a PhD, you can help spread the word and how to say, quell the fake news as well. Because if you ask the everyday person on the street, you know, about PhD, basically their reaction would be PhD is a lot of studying. You know, if you are very good at studying, right, which you like, if you like, you know, doing a lot of homework, right, then you know PhD is your thing, you know, which is not true. Of course, you know, there is this component to a PhD as well, right? But there is also, you know, let's say scientific communication, you know, which is writing and speaking, right? There is also traveling, you know, you get to go around and meet a lot of people. There is collaboration, you need to know how to work very well with people. And I think that these very important aspects of the PhD education are often overlooked. So I would say that for those of you interested in PhDs, right, first thing is to make sure you have a good idea of what the PhD demands, you know, right? It's also wrong to say, well, I'm very good at math and science, but I hate languages, so therefore I'm doing a PhD in engineering, right? That would be the wrong kind of mindset as well, because you need to be a good communicator. to be able to do well in science. Yeah. So besides that, I would say as an undergraduate, you have lots of undergraduate research opportunities here at NTU. You have Europe, you have Eureka. In EEE, we have this thing called the Research Assistantship Program, for very good students to directly work with faculty on challenging research problems. So do not be shy about reaching out to faculty and asking them, for research projects they might have. Yeah, so that's it.
Thank you very much. Okay, if there's no more question, I think we can share the QR code for the attendance. Yes.
So thank you very much, everyone.